Hello everyone, my name is Prakash. Uh, let's get started with the second session on static timing analysis. In the first session, we have discussed about Liberty format and how does a Liberty format represents combinational cell delay, slew, transition time, and all the relevant data. Let us now discuss about the sequential cell. So So let us assume this is an example of a D flip-flop. So this is a D flip-flop with D, clock, Q, and let us assume these are the set and reset pins. Now a sequential cell can have many timing arcs based on like whether the pins are treated synchronous or asynchronous. So let us first categorize like which of these are synchronous. So in our case, synchronous one is only the D. So the change of D, so whether the D can change, is controlled via clock. So for this we know that with respect to the clock edge we have a relationship that the D should not change. If the clock edge is at this point, it should not change sometime before and sometime after the clock edge, which is noted by setup and hold time, correct? So in the Liberty format, when we see, we'll see this particular relationship getting captured. So with respect to clock active clock edge, we would have a setup and hold mentioned with respect to D pin. Now this is synchronous. There could be like synchronous enable, synchronous set, synchronous reset. Depending on which cell are you referring to, you might also see those synchronous paths also mentioning the setup and hold requirement for these respective pins with respect to clock. Now, now we say that when the clock edge occurs, the latched value or the internal latched value would get propagated to the output, correct? The stable latched value would be propagated to the output. So there is certain amount of delay from the clock to the Q, that is called T clock to Q, correct? So that value also will be mentioned like this particular delay are correct. Now this is also with respect to clock, but this also has a synchronous relationship, and then this is with respect to output pin, and these all were with respect to the input pin. Now coming back to the asynchronous pins like set and reset. So we know that asynchronous pins can cause the output to change combinationally, correct? So this set reset uh, will make the output to go high, or this reset may change the output to go low based on like how this set and reset combinational path is formed of, correct? So there can be a independent timing path from this R to Q and S to Q. These are called like a reset output path, correct? From so R to Q, you can say just for naming for our purpose, R to Q and S to Q. These are delays from S to Q and then R to Q. Now when the asynchronous pins get asserted, it can simultaneously after a certain amount of delay it can change the output pin Q. But when the asynchronous pins gets deasserted, okay, the deassertion can happen quite close to the clock, correct? Now in that case, the once the deassertion of asynchronous pin occurs, the clock has to take over and and follow the synchronous behavior and continue the synchronous behavior. In that case, if these pins are changing very close to the setup, very close to the clock edge, there could be a violation again on the output. These are called recovery and removal violations. Okay, so we have setup and hold on the synchronous pins. We have delay pass from clock to Q. We can have delay pass from S to Q, all the asynchronous pins to the output, and also we have a recovery removal checks for asynchronous pins. All this we'll discuss in the subsequent slides. So, so let us assume this is our D flip-flop from the previous ones. For simplicity on this slide, we are concerned about setup and hold, so we have not taken into account the asynchronous signals. So let us assume this is D prime and this is clock prime, and this is the clock. Sorry, this is the D and this is the clock. Correct. Now we know that standard cell library would provide a relationship between, so if this is clock prime and this is d prime, so relationship for setup is this particular time, correct? So t setup, which will be how, what is the forbidden time in which the data cannot change for this particular pin, correct? Now in this circuit we have added some combinational path. Let us assume that we like we could make this logic, or we could have some kind of scan or like some other cell, or in a circuit level representation when we have our D flip-flop instantiated, there can be a clock path delay or the data path delay. Let us assume that this data path delay is T data and this clock path delay is called T clock, correct? So this is clock. Let us again write it again. So we said that this is D prime, this is clock prime, and this is D, and this is clock, this is T data, and this is D clock, correct? Now we are saying this is clock prime, and then this is data, sorry, D prime. So earlier the relationship of setup and hold was here. So this is still the setup and hold relationship with respect to this D prime and clock prime, correct? This what I mean to say, the flop with respect to this flop, this is the setup time, but the actual D prime and clock prime would be skewed by this much amount, correct? So this, but now assume that this delay is T clock. So the actual active clock edge gets skewed or delayed by this much amount. So the active T clock prime would happen here, correct? Simultaneously, there is some data path delay which can cause the data to be also skewed. So data is getting delayed from here to here with the T data. So this was the original data, and we say that the skew between these is T data, correct? Now the setup and hold violation would has to consider with respect to these pins, correct? So this particular path, or in the waveform, if you see with respect to this signal and with respect to this signal, correct? So active clock edge for this is here, correct? And the change of data is happening here, correct? Now this library would have a setup time of TSU. We need to make sure that this change, this if the setup time is smaller than this stable value, then we are okay. But if the setup time is larger than this stable value, then there is a violation. Okay. So for that we introduce a terminology called data arrival time and data required time. So for all data related paths, we'll say data arrival time, and for all the clock related paths we say as data required time, DRT. Now in this context we are only looking at this circuit. Now data arrival time, data required time can be computed. It's generally computed from the launch clock. The data arrival time is computed from the launch clock edge, goes via clock to queue delay, and then the data path delay. And data required time again is with respect to capture clock edge, again the clock path delay, and then the respective clock which gets hit here. Okay, but in this case the data arrival time is this and data required time is this. Now for setup to meet, what we are trying to say is this delay, correct? So if we say data required time, correct, this particular thing minus data arrival time, correct? So what we are saying the clock should come sufficiently after the change of, when the last change of data has stabilized, correct? And that last change of data stabilized should be greater than T setup. Right? So this is basically the setup analysis for this particular circuit, and then we'll reuse this like this data arrival time, data required time terminology going forward. So again with respect to hold, we see like this is active clock edge and data starts changing here. Now we need to check whether like this change of data is happening after the hold requirement or not, correct? And that's the basic the hold check. So again, in this case, we say this is the t data delay, and this is the t clock delay, and this is d clock, d prime, clock prime, and then this is q, whatever, correct? Now the requirement, again the check is happening at this, like the clock prime with respect to this, correct? So if you say this is clock and this is clock prime, so this is our reference clock edge or the actual capture clock edge which will get analyzed for data violation with respect to this pin, correct? So this is d and this is d prime. So our reference clock edge, if we split it like this, so will be with respect to this, correct? Now again, this path delay we are saying it's data arrival time, and this path we are saying is data required time, correct? So in this particular case, the if you see what do we need? We need that the data change should come sufficiently after the clock age occurred, correct? So data arrival time, so this is measured by data arrival time, correct? And this is measured by data required time, correct? So what we are saying, data arrival time minus DRT should happen sufficiently after the hold window, correct? Got this? Yeah. Having analyzed the setup and hold requirement for this circuit previously, now let us see, we might have always heard whether like, or we might even been asked in multiple interview questions whether the timing checks can be negative, the setup can be negative, the hold can be negative, or like, so we know that setup and hold are just the checks with respect to edge. And then let us assume this is the standard cell from the library which has a setup and hold of 1, correct? Now this is fixed, correct? Now this library itself may incorporate this methodology what we are going to discuss, and then provide cells which are like setup optimize or hold optimize, right? But for this example, let us assume that this particular cell has a delay of 1 ns, sorry, setup requirement of 1 ns and hold requirement of 1 ns, correct? And we are trying to make a cell which is optimized for setup and which is optimized for hold along this dotted boundary. Let us call this as DFFS, or and then the other one as DFFH for hold optimize. Okay, we'll see each of these. Now for the nomenclature of this, we know that from our previous example, this is D prime, this is clock prime, and the setup and hold checks are actually performed at these points, correct? And now we are saying this is our D, this is our clock, and this is our Q. So what we are trying to say that we are trying to create a flop which is at this dotted boundary with interfaces D, clock, and Q, correct? And then we are trying to see whether like we have a setup time of 0 or negative and hold time of 0 and negative, correct? So let us nomenclature this cloud delay as T data and this is T clock. Now, so we know that this particular circuit was D prime, sorry, clock prime, D prime, correct? And this was 1 ns, 1 ns. Don't like forget about the scaling of this. Yeah. So now we know for setup, we know from previous slide for setup requirement, data required time minus data arrival time should be greater than equal to TS, correct? For this particular example, it is data required time is like T clock minus T data should be greater than equal to 1 ns. Now let us consider various conditions like T clock of 0, 1, 2 and T data of 0, 1, 2 in some combinations, okay? For the first one, let us assume that t clock and t data is 0, correct? So we are saying t clock delay is 0, t data is 0, which basically means like it becomes the previous circuit, correct? In that case, you will see this 0 minus 0 greater than equal to 1 ns. So 0 greater than equal to 1 ns. So we see that we are off by 1 ns, and that 1 ns was the setup requirement which we have not met. So this particular circuit will violate by 1 ns. So if we make a circuit, this D flip-flop, this dotted flip-flop, with just a wire connectivity between these without any combinational skew order clock or data path skew, then it will behave exactly like the previous circuit of setup requirement of 1 ns. Got it? Yes. Now let us assume the clock delay to be, now from, let us take figure out a number from this and then take that example. So to improve setup, what do we need? We need this particular value to be greater than 1. So there are multiple things what we can do. Either we decrease the data path delay, so either we decrease the delay across this particular combinational cloud, or even if we increase the clock skew or clock path delay, then we'll get a value of which can be greater than this, correct? In that case, we can say that our circuit meets timing, correct? Let us assume that our data path delay is 0. So we are saying data path is 0 and the clock path is 2. So in this case, from this equation, if you see 2 minus 0 greater than equal to 1 ns, so 2 greater than equal to 1 ns, correct? So we are seeing that we have a margin of 1 ns if we have a circuit in which the clock path has skewed by 2 ns and data path is not skewed. So it is equivalent to this being directly connected and the clock having a skew of this. So if you see this, we have a margin of 1 ns here. So that results in a negative setup check, correct? So now what if this particular delay, what we are saying that, let us assume a case where the clock skew is 1 and then the data is 0. Then in this case, we can say that 1 minus 0 greater than equal to 1, and then it exactly meets. So we would have reached a scenario in which this particular the setup requirement of 0 for this combined circuit, correct?
So now let us take a case for hold analysis. So what we are trying to say is, so this was D prime, this was clock prime, and this was D, this was clock, and we said that T hold was 1 ns, and we are trying to optimize this flop for a hold time now. So this was D data and this was T clock. Now from the previous couple of slides, we know that the data arrival time minus data required time should be greater than equal to the hold. So in our case, it would be data T data minus T clock should be greater than equal to 1 ns. Now from this equation, we see like to optimize the hold time, what do we need? We either need to increase the or decrease the clock path delay or increase the data path delay. So let us assume from the previous, like the similar tables, like let us assume the T clock was 0 and T data was 0. So in this case, again, this will become 0 minus 0 greater than equal to 1, and then it will 0 greater than 1. So it will violate by 1 nanosecond, and this particular circuit will behave exactly the same as this particular uh, flop, correct? Now, what if the T clock is 2 and T data is 0, correct? So in this case, we'll have 0 minus 2 greater than equal to 1, and we see that we are even more like, so if you see the difference between this, now this is violating, like earlier it was only violating by 1 ns, now it's violating by 3 ns. So if you see, if we increase the clock path delay, the hold has worsened by 2ns. The hold requirement for the combined circuit would be 3ns if we take this scenario. Now what if we increase the data delay for this? So assume the t clock was to be 0 and t data was 2. So in this case it will be 2 minus 0 greater than equal to 1, 1 greater than equal to 1. So in this case if you see we are matching the requirement for our hold, correct? So this is the exact, so yeah, sorry, this is wrong. So this is 2 greater than equal to 1, so we have a margin of 1. So the whole improvement is like that, like we are even allowed to change 1 nanosecond before the clock edge. So this results in again a negative hold time, correct? Now for the simpler case, like if you make it to, now if you take the other case like t clock equal to 0, t data equal to t data equal to 1, then it will be 1 minus 0 greater than equal to 1, and then 1 greater than equal to 1. So what we are saying, when we have a data path delay of exactly 1, then we would exactly be meeting the hold requirement of 0. So these are the cases, like it's all depends on the data path delay and the clock path delay, what would be, and depending on that our setup and hold requirement would take into effect. So let us now move on to recovery and removal paths. So we have said earlier that, so let us assume this is set and this is reset and this is Q out. So we have earlier said that this reset can cause the output to change via this combinational path, and then similarly this set pin as well. Now this is fine, the assertion is fine, because the assertion, the moment this reset gets asserted, it controls the value of Q, and then we don't have a problem. The problem occurs when we have this reset assertion or this set, like reset deassertion or this set deassertion, very clock to the active clock edge, correct? So that's the thing. So recovery, what it says that, okay, now just to state here, because we have active low, so these are not, so active low. So at this point of time, this asynchronous signal was asserted. So with this call, we say that this was asserted, correct? And then this deassertion of this asynchronous signal is happening at this point. And after deassertion of this asynchronous signal, the clock has to take path of the data path control, and then it has to update the queue based on its value. So now, so recovery means like after I remove the reset, correct, or after I have removed the asynchronous assertion of a signal, how much time it takes for my circuit to recover, correct? So that is measured by the recovery time. So recovery time is the time before, the time between the deassertion of a reset and the assertion of the active clock edge. So this recovery and reset and recovery and removal times are specified in Liberty file for all the asynchronous inputs. So removal is again like a kind of a hold check, in which like, so again, because this was active low, we are saying that this asynchronous signal was asserted during this entire duration of time, and we are trying to deassert this. Now again, when we're trying to deassert this, it should not happen as close to the clock edge, correct? Similar to the hold time. So that controls the removal check. So removal specifies that what is the time between the clock edge and when I can safely deassert my reset or the asynchronous signal. So that is called a removal check, and we'll see this data also being specified in the Liberty min pulse width. So Liberty file also has min pulse width specification for respective asynchronous or clock signals. So mean period width or mean pulse width. So these are the various categories of that. So in the first session we have discussed like some inertial delays and transport delays, correct? So we have seen that if the inertial delay of a circuit is like 5, and then there is a signal change which is less than the inertial delay of that of the gate, that change is eaten up by the cell, correct? So that is again the same thing, like, so this specified mean pulse width space is kind of a inertial inertial delay check for respective gates. So in this case, this whenever this asynchronous signal changes, we should be able to propagate this to output. But if the change itself is very small, if the change itself is very small, and the minimum requirement is this, then this change might be eaten up within the cell and then might not get reflected into the output. So these are also these are some more category of checks which are performed on the asynchronous signals. So now let us see the liberty format of this. So our D flip flop is called DFF SR. So DFF set reset. And then again, if you see this, so how do we know it's a D flip flop? Again, in case of combinational circuit, we had a function, correct, which used to specify a b bar or something like that. In this case, like it's mentioned like this. So FF is a flip flop, and then like we have next state. Next state is the D pin. Clock down is the clock port. Clear and preset are like active low. We can see this is active low, not of R and not of reset. So now if you take this as a reset, this is the clock pin. So the clock pin again will, so this clock pin will provide a input capacitance to the previous gate, whichever is the skew or buffer or whichever is in the clock path. So this is the capacitance, like nominal capacitance as well as rise and fall if somebody wants to compute this separately based on the, so when I say rise and fall capacitance, again it matters. Okay, like what I'm saying is, suppose I have an inverter and then this particular node can change from 1 to 0 or 0 to 1. Depending on that, it might have to charge a different set of capacitance. That might not be very significantly different, but it can be, correct. So depending on that, like during the compute during the propagation delay computation, we would actually consider the delay based on the transitions, and then based on that we would suppose this node is going into a fall, then we might want to consider a fall capacitance charging time, and then based on that we might want to consider like something like that. So this pin, and then so in most of the cases we have seen the pin definition. A pin can be input port or output port that is specified by this direction, but then how do you know that this pin is a clock pin? So there is an attribute called clock. So for all the sequential cells, you will find this attribute which specifies what is the clock pin. And then again, like we discussed in the previous slide, minimum pulse width requirement, again like pulse width high and pulse width low, these are the minimum pulse width requirement which is needed for it to capture the change and then reflect at the output. So the input pin D, so like uh, as in other cases, like this input pin specifies the direction. So sorry, so this, the direction of this is the input, like D pin is the input, and then we have the capacitance specified, the the input capacitance which the previous stage would see. So the internal power, like the power dissipate, like the power specification here, and then okay. So this is our like point of interest for this session. So there is a term called related pin. So a flop has this port, and then we are trying to specify that okay, this timing on D, what we are going to see next, is based on this particular clock port. And then we see that the timing type, this is very important. Now so how do you know that this is like rising edge or falling edge, or like what kind of flip flop? And then so this specifies that okay, this is a whole time measurement, and then this was done with respect to the rising edge of the clock. Then as in previous cases, we might have seen like rise and fall delays. The rise and fall delays are with respect to rise and fall transitions at the D pin. Here you might notice that the hold time requirements, like some of the values are 0, which means that hold time can be negative. It's not a theoretical thing. In actual, the hold time values can also be a negative value. So again, this is just like again the setup arc, setup rising. This means that the setup value was characterized using the rising edge of the clock, and again rise and fall constraint for setup as well in most cases. So Yeah, so basically the timing window between, like, if you add like setup and hold, that some value would remain the same. So if you try to improve setup, the hold might get worsen, or if you try to improve hold, the setup might get worsened. So the effective window remains the same. Where which one do you prefer? That again depends on the methodology what we are working on. Now this is the output pin, and then this is the output. As discussed previously, the output pins doesn't specify any output capacitance, and then this max capacitance is used to like derive what is the maximum load this particular Q pin can see, and depending on that it can compute the maximum fan out for this. Now again, if you see the timing of this, like we have specified, this timing is with respect to clock port. Now when the clock age occurs, then again this, if you see, timing type is again rising age specified here, which means that this particular value what we are going to discuss is measured with respect to the rising age of the clock. Now again, if you see, the timing sense is non-unit because any age can cause a value of 0 and 1 at the output, and that is independent, like it is dependent on the D pin, but that D pin is latched within our network, and that the last value will be available at the output after clock to Q delay. So that clock to Q delay is basically this value, cell rise, cell yes. So this is the like rise delay for like the clock to Q delay for this particular cell. So, and then this is again the rise transition, like that, like the rise transition delay for that particular change. So whenever we see a clock, the output Q can go for a, like the output Q can change high or low, and not non-unit means that it can be different, so it can be any value. And then specific based on that we have specific, like this library has specified the clock to Q delay for this, and then what would be the output transition at the Q pin. Okay, now if you see this, this we are trying to see a timing for with respect to R. Now we have said that the Q pin was a, like we are talking about a this Q pin which can be changed via S and R. So this specifies the relationship of this Q pin with respect to R. So this related pin specifies that this is this. And positive unit means that a change in this will cause a positive change here. A rise in this will cause a rise in here, and similarly a fall in this will cause a fall in this. And timing type is called clear. Clear indicates that this is the clear port, or a, and then we know that this, but if you see, if you go before, we have seen that this was an active low port, so that a fall in this will cause a fall in this, so it becomes a positive unit and a clear port. Now depending on this delay, there can be a like the delay from this to this port that is specified using this cell rise, cell fall, and similarly the output port can have rise or fall transition based on this. So these are the rise and fall values. Similarly for set pin, like it's a negative unit and active low, so, and the timing time is called preset. Preset means we're setting the output value Q of Q to 1, and then if you see, like when we are setting this active low, then we are saying active low, so that when we make that set pin to low, the output pin becomes 1, so it is negative unit. And similarly, like in other cases, we see the rise and transition time specified. Now coming back to, so we have also discussed like this set and reset pin will have a reset and recovery check with respect to the clock port, correct? And this is what is specified here. So this pin is R, so this is the input pin, so it will have a direction as input, the input capacitance. Again we discussed there can be inertial delay, so for that we have a minimum pulse width requirement here. And then we go to the timing. The timing specifies that this particular timing is measured with respect to a clock, and then recovery rising means, so this is the recovery check for rising edge of the clock. So that's the check here, and then these are the values what it has to check. Similarly for S recovery rising, like yeah, so related pin, and then removal, like this is the recovery check, and then this is the removal check, in which again the related pin is clock, and then we see the respective value specified here. As as seen for like reset, this is for set. So similar template follows. Now state dependent models, we have discussed this in like this is similar to a non-unit case, correct? So when we have a XOR or XNOR gate, what we are saying that when A and B and Z, so we are saying a delay from here to here is dependent on this particular node. So in some previous Liberty examples, you might have seen some specification of when. When means like this particular measurement was characterized with this particular node as 1 or 0. So that values are like these are the state dependent models. If you go below, go before, you might have seen this like this. So this is the thing what we are talking about. SDF condition is basically the same when condition, but this is used for SDF generation. Okay. Now in previous last lecture we have studied about slew derate. Slew derate was term in which we measured because of the like a deep submicron node, we might have measured the like slew value across 30, 70 reference thresholds. But then we want to what we want to either characterize or that provide a number in 10, 10, 90 or 2080 format. So that then we give a derate value which will allow the tool to scale that delays value to the respective formats. Now there can be process like PVT like derate values also specified. So there can be temperature like so suppose we characterize a library at 125 degrees centigrade and then for a smaller variation like for like 120 degrees centigrade, like for a smaller variation we might want to, so they might have measured this library, characterized this library at this, and they would have run the similar set using 120 degrees centigrade, and then they would have computed a scaling factor. That scaling factor is basically derate for this temperature. Similarly, it can be done for the temp process and voltage, like slight variation in. So these derates are like not to be applied across. Like suppose I measure something as 125 and then I want to derate and using derate it for 75 degrees centigrade. That would not work, correct? For a simple slight variation of temperature, voltage, and parameters, the this was the uh, delay value which was extracted via the lookup table, and then based on the derate value, correct, these are the constants which are like the derate scaling factor which is used, and this is the characterized like for our example for temperature this was 125 degrees centigrade and then we are trying to measure for 120. So, so so that when we have a like this is the equation in which the tool uses to compute the actual delay values with for the specified temperature, voltage and process, and that values will actually be used for static timing analysis. Okay, now having all discussed all this, like let us analyze the setup and hold requirement for this particular circuit. Okay, so like there are a couple of things like terms what we are going to use. The first one is a launch clock age, correct? Launch clock age is basically the flop which is generating a data, and then there is a capture clock or a capture clock which is actually sampling the data. That's the as simple as that. So in this circuit we can see that this particular clock port, if you say this is the clock, this comes here, this gets divided into clock and reset. Sorry, this get divided into two parts, clock and then this path. So this particular so so delay between from this the common segment, and then delay from here to here, then clock to Q delay, the delay now from this point to this point, which is our data path delay. It could have various paths, correct? It could have paths from, it could go via this path, it could go via this path, and like many cases, correct? In case of clock, this clock will go via this path. That if there was certain other like path existing, then it could have taken that path as well, correct? Now we have discussed like the concept of data arrival time, correct? Data arrival time is basically this, like from the clock definition point, we take this path, the delay across one segment one, the delay across segment one, delay across segment two, then clock to Q delay, correct? and then we take this. Now this data arrival time, correct? This this network delay changes between setup and hold requirement, correct? For setup we might want to check the maximum, for hold we might want to check the minimum, and vice versa for this. So we'll see into details of that. Now we are trying to do a setup analysis for this. So we are saying the data arrival time for this particular gate. This is the segment 1, segment 2, clock to Q, CQ, and then 1, 2, 3, 4, 5. Now if you see the our requirement for setup was data required time minus data arrival time should be greater than equal to the T setup, correct? So so for for analysis, what we want to try, we want to make sure that this equation doesn't assume true for all worst conditions, correct? So what can be the worst condition, correct? The worst condition can be we can increase this delay as much as possible, decrease this delay as much as possible, and still meet the setup requirement. If that occurs, then we can surely say that this particular circuit meets the setup requirement, correct? Now in that case, so what we are saying that delay, we have to increase the delay across all the DAT, means the max paths, and we are trying to decrease the delay across the data required time, which is called the mean path, correct? So this so what I'm saying, like, so from this point to this point, there like there are multiple paths, correct? For setup requirement, we are going to take the worst case max delay path. So that path is basically, if you see from the circuit, it's 1, 2, 4, and 5, correct? So segment 1 delay, segment 2 delay, T clock to Q delay, plus uh, combo 1 delay, plus combo 2 delay, plus combo 4 delay, plus combo 5 delay, correct? And these all so this is the setup, the sorry, the launch data arrival time at this point, correct? The data requirement time would be now this delay, correct? Now in this case, this is a single path. We are not considering for this example that each gate can have like max and like based on the transition, the delays can even be different, and then like we are assuming that each gate get to have similar delay for like rise and fall. So for this, our this would be 1 and this is 2, correct? So this will be 1, sorry, this is segment 3. So S1 plus S3 plus gate 6 delay plus gate 7 delay, correct? Combo 7 delay, correct? Now our requirement would be this minus this, sorry, DRT minus DAT should be greater than equal to T setup. This is fine. Now the point is, like, is our this computation correct? So this is not correct. Why? Because we have said that our setup analysis occurs on the subsequent clocks, correct? So if the data launching is, so suppose we assume that this particular path, the path from this one was launched at clock 0 at time t0, and the clock period was like t, correct? Then the capture clock would start at 0 plus t, correct? So this effectively will now become, data required time will become t plus all these values, correct? Now that DRT minus DAT should be greater than equal to setup for this requirement to match, correct? So that's the thing. Now let us see for the hold. So for hold, we have seen that DAT minus DRT should be greater than equal to T hold. So in this case, like if you want to see the worst condition, what we are trying to, we want to increase this path. This can be a max path, and we want to decrease this path. So this has to be a mean path, and then still see that this particular thing meets the requirement. So in this case, this is segment 1, segment 2, clock to Q. Again this, so the shortest path, the minimum path would be via this path in this case, correct? So the DAT would be uh, segment 1 plus segment 2 plus T clock to Q delay plus C1 plus C3 plus C5, correct? DRT would be, now in setup we said that the setup analysis occurs between different clock edges, correct? but the hold occurs for the same clock at different flops, correct? So in this case, the launch and the capture clock, if the launch was at time 0, the capture would also start at time 0. So this will be like the again 0 plus the segment 3 s s1 plus 0 plus s1 plus s3, then c6 and c7, correct? Now based on this, we now this the hold will require that drt minus, sorry, data should come after all this combination, the data should still come after the data required time by t hold, correct? You get this idea, correct? Now what we are trying to say, that what happens when the skew occurs, correct? Now let us see the hold. And so data required time minus data arrival time should be greater than equal to t setup. Data arrival time minus data required time greater than equal to t hold, correct? Now in case of setup, what we are trying to do, we are saying that the data for our analysis purpose, we are trying to say, what we are trying to do is we want to increase this. So this is max and this is min, correct? And for hold, we are trying to increase this. So this is max and this is min, correct? Now the clock skew can be okay. So there can be like circuit like this as well. It's not necessary that the destination path will have a skew. So this clock network can come here, this can come here, this can have different buffers, and this can have different buffers as well, correct? So if even this path can have less skew, this path can have more skew, vice versa, correct? So what we are trying to say now, how do we account for this skew in our analysis, correct? Now in our case, what we are trying to, for setup, we are trying to decrease the clock path, correct? We are trying to delay the clock path as much as possible while reducing the clock path as faster as possible, correct? And still meeting the setup. So in this case, the ideal thing would be to compensate that skew on the clock path, correct? So what we can do, suppose like assume without skew, after all max delays the data was here, and after all min delays the clock was here. So max of data, mean of clock, correct? Now if we add the skew for setup analysis, the clock would get delayed further and would get more margin, correct? But the slew can be any value, correct? The slew can be, and what we are saying here, the slew at the synthesis stage, not like a post placement and post CTS. Post CTS actual slew will be computed, correct? We are, when we talk about skew like skew here, what we are telling here is like what is the amount of uncertainty we have to encompass within our design for it to work later, correct? So that's the margin we are trying to find out here. But after clock tree synthesis and after the actual the circuit is in the physical design, we need not estimate the skew or provide margin for the skew, correct? The skew would already be actually implemented, and then actual values will, the propagated clock would be used for that computation. Now for our synthesis purpose, like when we have to estimate a margin, suppose we estimate that the clock network can have a skew of 0.5 ns, correct? For setup, we don't want to delay the clock. We want to again pull the clock as close to this data and then make it fail, correct? That's our intention, correct? So in case of setup analysis, the slew values are subtracted from the clock path, and then the resultant clock is then checked for setup requirement. Got it? Now coming back to the hold. In case of hold, skew, sorry, like in this slide, if I have told slew, it's always skew. It's my, yeah. Uh, so in this case, if you see the skew, what do you want here? Correct. So for hold to fail, we want, so this was the requirement, correct? So we want the data to come as late as possible and the clock to come. So the clock path, this is max clock, correct? and this is max data, sorry, mean data. So we have tried to make clock come as fast as possible with adding more delays in the clock path, correct? And then we have checked that we still meet the set like a hold requirement, correct? Now in this case, where do you want to add the skew, correct, or subtract the skew, whatever be the case? In this case, if you see, the worst case would be we want to narrow this dimension, correct? We want to do this. So what in this case what we will do, we'll add the skew so that the clock comes slightly later, so that the margin of the hold requirement becomes more constrained. And then, so in case of hold, you will see that the skew value is getting added to the clock path, the data required time path, and then that value, that resultant edges are then compared for the hold analysis. Now there can be various uncertainties, okay? There can be uncertainties because of the clock path skews. There can be uncertainty between like subsequent edges of the clock because of the clock's jitter, and there can be some process variation for which we have to keep a margin, correct? So jitter, what we like, jitter is like periodical like temporal variation, correct? So temporal variation across like subsequent clock edges. So again, what we are trying to say here is like my first clock, like the first clock period was 5, the second clock period can be 5 plus minus based on the ppm, like some variation on the clock period. Again, for setup we want to decrease the clock period so that it becomes restrictive, and for hold we want to increase the clock period so that it becomes the data required path, we want to increase this value. Okay, now do we actually need to add the jitter to the okay, so to whatever I said, like for setup what we are going to do, we need to like jitter would also be specified in some like ppm or some percentage of the clock period, correct, some 10% or whatever. So that we are again going to, for setup, the thing was like this. So the maximum delay and the minimum delay here, so we are trying, we we said that we'll delay the jitter value from the clock so that the clock becomes slightly much ahead, and then we'll try to make sure that this maintains the what you call the setup requirement. Now in case of hold, in case of skew, what we did, we added to the clock path so that the clock path and then we analyzed like that. But in this case, if you see, jitter is like period to period variation. Okay, so first period can be of 10, the second period can be of 10 minus 10 plus minus something, the second again be 10 plus minus something, correct, the plus minus 5%, correct. Now across two different periods there is a variation, but within a period it is fixed, correct, the clock period for that particular cycle is fixed, so we don't need to account jitter for hold checks. So that's the summary for this. Let us spend some time now to analyze between differences between STA and GLS. So STA basically computes all the static paths and then tries to see that the delay, all the transitions are stable or have arrived before the setup and like hold, like within the setup and hold, no active transitions should occur. But gate level simulation like works in a different manner. It actually ensures that during the setup and hold window of that particular clock, there should not be any transition. Like the two statements might seem similar to you, or you might have heard it similar, but that has some differences. Let us review that. So so let us assume that so there is a clock. So so this clock period is 10, correct? We are saying this is 10, and the launch occurs here. And let us assume the setup and hold for the FF2 is, so setup is at 1ns and hold is at 1ns, correct? So from this 1ns, so there should not be any change, allowed change between this duration, correct? So now if I say my launch to this particular deep in delay or data arrival time is 13. So if I say this is, then if it is 10, then this is 9, this is 11, 13 is somewhat here. So my change is arriving here, correct? Correct. So in case of simulation, because this change occurs outside of the setup and hold, a GLS would be clean, correct? But from STA perspective, we have seen that okay, so the launch takes like the data required, and so data arrival time, this is the data arrival time. Data arrival time is 13, correct? Data required time is 9. So 13 minus 9 should be greater than equal to 1, which is the setup requirement, since we are talking about two different clock edges, correct? So 13 minus 9 is how much? Sorry, the clock is 10. So this is 3 greater than equal to 1. So we see this particular setup is getting violated by 4NS. So we would see a setup violation in STA. But if you simulate this particular scenario in GLS, it would be a clean. Now again take the same clock. So we had the same clock. So this particular 1NS here and 1NS here was the forbidden zone, correct? And the delay is 10.5, correct? In this case, 10.5, if this is 10 and this is 11, 10.5 would be something in between. So we are saying the data change in between this, correct? Now when I say a data change is in between this is within the meta stability window for this like for this flop, correct? This would what this would mean is that there would be a hold violation in the gate level simulation, because it would see that the data is changing within this window. But again, from since we're talking about two different clocks, again the data required time would be 10, data arrival time would be 10.5. So and then we are saying that data required time minus DRT should be greater than equal to 1 because of our flop has 1 NS. So this would be 10 minus 0.5 greater than equal to 1. So with that this doesn't meet, correct? So sorry, 10.5, so it's minus 0.5 greater than equal to 1 NS. So with that we see that this particular scenario results in a setup violation in STA and a hold violation in GLS. Now, why are these occurring? This is occurring because the simulation tool is dynamic. It just ensures that the window is clean. It doesn't ensure that the data is actually captured correctly or not. That it cannot. So that is again taken a functional. Like if this is the case, you might not see a setup and hold violation, but you might see a functional like failure as well. You might see a test case fail. But debugging the test case fail might be difficult. And obviously this would not occur between race to race paths like intermediate. So there are like multiple cases you might have to be careful if the frequency is not met. If STA is not clean, you might not even want to take it to a GLS, correct? So that's that. So only a STA clean design should be taken to a GLS, so that any functional failure would be with respect to the wrong transformation of synthesis or some transformation like that. Now, now for a hold while, let us take scenarios in which we are considering the hold case. So hold case occurs between the same clock edge, correct? Now we are saying that this is the clock. So this clock is reaching both the flop, FF1 and FF2, correct? Now in our case, let us assume that our clock is significantly skewed, correct? So when I say that clock is significantly skewed means, and then let us assume this is a shift register back to back flops, correct? So there is no data path delay on this D pin. So what would happen in this case? Your change, since the suppose this was the actual clock on FF1, because of the skew FF2 would see a clock here, correct? Now change from FF1 because of this like no combo path here would reach in between this boundary, correct, at FF2. So this will result in a hold violation for FF hold violation of FF2 in STA. Now again, if you see this circuit for gate level simulation, what it will see that there was a metastability window, and this change was falling within the setup window, correct? So it will flag a setup violation in GLS. So again, this is a mismatch here. Now there is a case in which, okay, in this case, correct? So again the same case. So this was the FF1 clock. So again, mind it that we are talking about the same clock, correct? So let us assume that skew was 2ns. So this becomes the FF2 clock, correct? This particular edge of the clock. Now the data was again like same from the previous one. This is a shift register kind of thing. So in this case, what we would see that again the data is reaching this particular. So if this change from FF2 will reach within this, like if this was FF2, the setup and hold window was like this, correct? But since we are considering the same clock edge, and that means the hold check, correct? In that case, the change of FF1 would be available within this boundary, correct? So again, it would like whatever be the delay value of the skew, same clock cycle check would result in this case for a hold violation in STA. Now, if you see this, if the delay was 2ns, correct? If the skew was 2ns and my change would have stable, like suppose here, correct? Then what would happen? This in the gate level simulation, because this was the boundary, it would not even see this change falling within this meta stability window or the setup and hold window. So in this case, there would be no violation in GLS, correct? So what we are trying to conclude here is like GLS can be effective based on scenarios like we might want to validate that our timing clean netlist is functionally equivalent. But verifying a non-timing clean netlist in GLS can result in false like setup, hold, or no violation cases, which can be pretty hard to debug. So you might be careful with that. So we have speak about SDF in briefly like so. So many standard cell library will give you a gate level model using a specific arc to arc delay like uh, a model like AND gate in which they specify from A to B, this is the delay, A to Z, this is delay, from B to Z, this is the delay. But then as we discussed, this is not like this is just like a modeling purpose. It might not involve routing or routing approximation or the placement approximation. So after netlist, the tool can dump out SDF, and that SDF can give you some kind of whatever constraints you might have provided, the delays with delays, and then the environment what we had set like wire models or wire delay models. Based on all this, it would dump out a delay file. This delay file is back annotated to the art like during the RTL simulations, correct? And then that this becomes like fairly accurate, and this is called full timing gate level simulations. So okay, now to summarize the static timing analysis, so STA we have seen that in no cases we actually required a time test vectors, correct? Based on the output like the launch path, the capture path, the data arrival time, data required time, we were able to validate, setup, hold, and similarly we could have done for recovery, removal, and other timing checks as well, correct? So in any case that we didn't require a timing like a test vectors, correct? So this so and then since we are doing it statically, we could have like we could always do on the entire circuit at the same time, correct? Because we break the entire netlist into timing paths, and then each timing paths are then analyzed independently, and then they are validated, correct? Now for timing improvement, there can be scenarios the tool want to move a register like retiming pipeline. Like these are the advanced concepts. But then again, the tool can change the timing behavior if a path is not able to meet timing, and then the previous path has a lot of slack, it might try to move a flop to that like slightly some combo can be reshuffled between these paths. So these are that. But then what we're trying to say is STA is exhaustive. Exhaustive means like we don't need to permute like we don't need to exercise all combinations of input patterns to sign off, correct? We can statically analyze all the timing paths and then say if all of them can meet worst and the best case conditions, then we are we can say that okay, we are good for this. But then STA only guarantees the frequency requirement, correct? It can say that this circuit would work at this particular frequency, but it cannot, because since we are not exercising any test vectors, there is no way it can validate the functionality, correct? So once we have a netlist which is functionally clean, we might want to take it to a we might want, like, there are different ways we can use a formal equivalence tool or logical equivalence tool to establish the equivalence between a RTL and a netlist, which is like yeah, like there are a lot of tools like commercial EDA tools that does that, or we might want to do a entire test case. Uh, we might want to run a like a get level simulations, correct? But again, running gate level simulations takes a longer time, and again, what if we have not exercised one particular scenario or test case, correct? So like there, it can so happen the transformations was okay for all the test vectors what we had checked, but there was one case which in which the RTL and the netlist is not equivalent. So actually the formal equivalence tool has gained popularity, and then it is used in most of the cases which to establish a relationship between any transformation. So this is all what we had for STA. I hope you have learned something and got to know some details. Thank you. Take care.